Hello, everyone. Welcome to the FieldView Auto Partitioner webinar. We're excited to share with you some of the work we've been doing with the Auto Partitioner in the last year. As we've been talking to customers, we've been trying to educate users on our MPI parallel capabilities that have been in FieldView for many years that could help you get performance speedups. But what we found is that there's bottlenecks. Either users have their data not partition at all, or partition in a very unbalanced way, which doesn't allow them to take full advantage of the MPI parallel capabilities. So what we've decided to do is think of ways we could partition data on the fly that will allow you to take full advantage of the MPI parallel capabilities. So we've decided to start pretty simple with structured data, particularly the plot 3D loader. And so we'll be sharing that today, and we're excited to share that with you today. My name is Raj Alimutu. I'm on the right here. I am your full account representative. Anything you need as far as technical question goes, if you want one-on-one meetings, set up meetings for your company, I'm your guy. So feel free to contact me directly if you have any questions about FieldView, anything FieldView related, and I'll be your moderator for the webinar as well. On the left, we have Yves-Marie Levebvre. He'll be doing most of the heavy lifting for this webinar. He is our Chief Technical Officer for our larger organization, but also the full technical contact for FieldView. And so he'll be running most of the webinar, and some of you may have talked to him already. With that, pass it on to Yves-Marie.
Thank you, Raja, and hello, everyone. So yeah, my name is Yves-Marie Levebvre, and today I'll be giving you more details about one new feature we've introduced in FieldView 21. If you're interested into learning all of the capabilities from that version, we have a separate webinar recording available. But today we're going to look more into the details of a unique capability that we call Auto Partition. To do that, we'll have to take a step back and talk about how FieldView does parallelization, the basic principles. We'll see that there is a challenge, as Raja mentioned already, when the partitions that are pre-existing don't allow FieldView to do good load balancing. And the solution we've developed is to auto-partition your data, so potentially repartition what you have. And we'll look at some benefits, some speed-ups on actual cases so that you can get a feeling for what kind of speed-ups you could get on your hardware and your data. So let's dive right into it. And so first, I need to explain how FieldView does parallelization. And to do that, I'll take a step back even further and talk about hardware in general. So on your systems, you typically have one node, if you have a workstation, where memory is shared between cores. And if you work with an HPC environment, your cluster has multiple nodes. So you can see more than two nodes, but each one has its own memory. So FieldView has two levels of parallelization to take advantage of this architecture. We use a hybrid solution with a mix of multi-threading and MPI, which stands for message passing interface. So we'll start with a description of what we use multi-threading first for. So when you run FieldView, for instance, in what we call direct mode, which is really serial, you have only one server process doing all the heavy lifting. In such a case, we are still able to use all the threads for some of the operations that FieldView does, such as computing formulas like gradients or Q-criterion, which can be CPU intensive. We use threads for spinning up streamlines computation as well, and other operations like that. But really, the heavy lifting with parallelization is done thanks to MPI, and MPI starts taking place as you have more than one process. So here, For simplicity, I'm showing 2 processes, but for most customers, they are going to be running 8 processes. And that's helping for reading your data, preparing it for your scene, computing surfaces. All of that is parallelized with MPI in FieldView. And on top of that, as you can see, each one of these processes is still using multiple threads when it does formulas, when it does streamlines. So again, we have this hybrid parallelization. What's great with MPI is that you can do parallel on a system with shared memory like here, but you can also go further and have processes running on multiple nodes. So again, here I'm only showing 2, but really people will be running a lot more processes on more nodes. And what's great with that is that it gives them access to more memory if they need to look at really large cases. Okay, so this is the logic for FieldView's parallelization. For the rest of this presentation, when talking about parallel, I will be talking about MPI parallelization. Next, some customers ask us, what kind of benefit can I expect from MPI parallel? Is it going to speed up my workflow? The first example I want to show here is from a customer who was trying the Auto Partitioner and giving us some benchmark results. And he was kind of disappointed by the speedups that he was getting. He was making still images for a steady state case using software rendering. So if we compare serial to parallel for his case, so I've mentioned that with MPI parallel, what's going to really be improved is the read time, shown with the blue bar over here. So by having a smaller bar, I'm showing here that the time is reduced. The coordinate surface creation, or word for cut planes in FieldView, this is accelerated as well, but to a lower extent because this is already very optimized in FieldView. But then in his case, most of the time was spent rendering those planes, especially with software rendering, which is very slow. And the rendering is not affected by MPI. Really what you want to do for having faster rendering is to move to a system with a GPU, a graphic card for doing hardware rendering, or moving to a faster graphic card, and then you're going to reduce the time spent on doing the rendering. So yes, in this case, parallel was bringing the overall time down, but not as much as moving to a better system for graphics. In a second example, now I'm looking at a case. This is an actual question we got in preparation for this webinar. One of the attendees asked us, well, I'm doing unsteady animations, can I expect benefits from parallel? And generally the answer is yes. When you do an unsteady animation, what you do is load a time step, create a surface such as this large ISO surface over here. You do the rendering, and then FieldView does the same for all the following time steps. So again, data input, ISO surface computation, they benefit really well from parallel. And in case like here, where you have a small amount of rendering, thanks to hardware rendering for each one of your time steps, really rendering doesn't dominate. And so you're getting to get a good speed up from using MPI parallel for an unsteady animation. All right, so that being said, let's go deeper into how FieldView does MPI parallelization. For our load balancing, for the partitions, we rely on the blocks you have in your solution files, in your mesh and solution files. So those blocks of cells that we call grids in FieldView are going to come in different sizes that I'm representing with this bar chart over here. And first, let's look at an ideal case. We have 8 grids over here of about the same sizes, and we're going to load them in parallel in FieldView. What FieldView will do is send one grid to each one of its MPI processes. And so now that I've introduced this logic of the 2 bar charts, going forward and looking at more complicated examples, we're just going to keep the 2 bar charts and making the assumption that the more nodes we send to a process, the longer it's going to take for it to do its computation. So then what's going to determine the speedups we can get thanks to parallelization is really what is the longest process, what is the MPI process that has the largest number of nodes to work on. And that tells me that in this case, again, an ideal case, I have a longest process that is about the same size as the shortest process. And so that's very good load balancing. I'm going to get a really good parallel speed up. Let's move on to a slightly more complicated case. Let's say that now we have 16 grids instead of 8. Again, pretty well balanced. So FieldView is going to do load balancing by having 2 grids on each one of its MPI processes. And again, everything is well. The longest process is about the same size as the shortest process. Good load balancing and good parallel performance. Now, it's not always the case that you have something ideal like this with good, relative sizes of your grids that are about the same. Your grids come from a lot of different reasons in your workflow. Maybe you have, like in the top right corner, maybe you have a structured multi-block solver with adjacent blocks. So really those grids are coming from your topology. Maybe you're doing overset with a solver like overflow, and then you will have large off-body grids in the background and smaller near body grids close to your geometry. Or maybe you're doing AMR, like shown over here, which leads to the creation of a lot of small blocks, and again, some larger big blocks in the background. So for all of these reasons, you're going to deal with something that is often not ideal. And so if we look at the case here, which is again 16 grids, but now we have just 2 of them that are much larger than the rest, it's going to be a struggle for FieldView to come up with a good load balancing. Really, the 2 largest grids are going to be each on one process. The rest is going to be balanced between the remaining processes. But because you have a much larger block, over here, your longest process is much longer than the shortest one, and that gives you pretty poor performance. And this is the main reason why a number of our users, when trying parallel, were telling us, well, beyond a certain number of processes running on a number of cores, I'm no longer seeing an improvement. So this is where we decided to implement a new solution that we call the Auto Partitioner. This is very unique. It is the first, FieldView is the first commercial post-processor to have such a solution. And the idea is quite simple now that you understand the challenge. The Auto Partitioner is going to split the largest grids on the fly at read time. And by doing so, it is going to create new grids. So in our example here, we've created grid number 2 and number 4, which then allow FieldView to add good load balancing with the longest process close to the shortest process. So FieldView does that again on the fly. There's no overhead, and either on time or memory. And FieldView really comes up by itself with this optimal partitioning. And okay, so thanks to the Auto Partitioner, now we again get good load balancing and good parallel performance for a case that is not ideal. So that was all these examples we were looking at parallel 8. But one of the benefits of the Auto Partitioner is also the ability to go up to higher core counts. If you look at the same grids and try to load that on 16 cores, the Auto Partitioner will automatically adjust and just create more partitions on the fly. And that will give us the additional performance that we are looking for working on a higher number of cores. So really, it is that simple. This is the main idea behind the Auto Partitioner. And so now let's move on and look at the actual benefits and the performance we get on some real cases. So the first one here is a bit notional. This is a single block in the Plot3D 3D format, 200 million nodes. And what's interesting with a single block is that, as you understood how FieldView works, in the past it was impossible to read that in parallel. So here we're looking at a comparison. On the left, we have FieldView working in serial, loading the single block. On the right, we have the Auto Partitioner breaking it down into blocks for the systems, which is running 16 cores. And so we're running a side-by-side comparison of interactive work, loading the case. So first the mesh, then the results, and loading a restart, so the work is done on the right, an isosurface restart for creating this sphere geometry. You can see over here through the CPU recordings, at several instances, we were using 100% of CPU. That's a really good sign. And that wasn't the case on the left side, and so the overall performance was much lower. So looking at real numbers, numbers that were obtained on a larger system, running in batch to have more accurate and easier to reproduce timing. Going from serial to using the Auto Partitioner on 32 cores this time, we had a 2.5 times faster operation for doing the same thing, reading the case, computing and rendering an isosurface for this dataset. So that's a pretty significant speed up. Some of you might be wondering why it doesn't go faster, why we're not closer to a linear speed up. We are always going to get some bandwidth limitation over here. In this particular case, most of the time then gets spent on reading the case. And there's going to be a bottleneck that depends on your system. Depending if you're reading on local hard drive, whether it's an SSD, whether you have a parallel file system. Each one of those systems is going to give you a different bandwidth, and the higher the bandwidth you can get, the higher the speed up you can get by reading a large file with multiple MPI processes. Moving on to a second case, this time more of a real life case. We are looking at a multi-grid Plot3D file, 17 grids in this case. So for topological reasons, 5 of them are really much larger than the rest. And so it meant that load balancing in FieldView was quite easy to do up to 8 cores, but then the performance was dropping beyond 8 cores. We'll see that in a minute. So doing the side-by-side comparison again, we are reading the mesh first. So it's slightly of a slower start on the right, as we had to specify that we are reading in parallel first, then reading the results. So it's already ongoing on the right. And you can see that we get spikes again with 100% of all cores working at the same time. Now loading the restarts. This time we are doing an isosurface of Q criterion, which is a pretty intensive computation and a pretty dense isosurface with a lot of faces. So you can see that all cores are working again, and in a few seconds we'll be done, while on the left, the serial job is still, we're just starting to call the restart. All right, it's done on the right. So we have this very nice isosurface, and it's going to take significantly more time on the left for it to complete. All right, so I'll just move on and we'll give you the numbers, again, obtained on the larger system, running in batch for better accuracy. And so we went from almost 180 seconds in serial down to close to 110, so 1.6 times faster running just on 8 cores. And as I was telling you, because of these 5 larger blocks, it doesn't make much sense without the Auto Partitioner to go to more cores. And so what the Auto Partitioner is giving us in this case is the ability to get additional speedups at higher core counts by breaking down those bigger grids and continuing to use parallel further. And that's also nice, again, if you're going to load such a large case on a cluster, accessing more memory from the various nodes that you have. So that's where MPI is very helpful as well. So just taking a second to further explain how you turn it on, since that was kind of quick on the screen captures. So you need to first be running FieldView in parallel. So to do that, you go to File, Data Input, you pick either the local parallel options, over here, local license parallel, or you go to Choose Server and pick one of your presets where you've defined what remote server you're going to run on. So the settings are captured in server configuration files, where you basically say on how many cores you want to run on, what protocol you're using for connecting to that remote server, where are the FieldView executables located, and so on. So you do that once and for all, you save that file, it can be reused by all your users, and it shows on the FieldView interface. So that's very easy then for all of your users across the company to use those server configuration files. So once you've specified that you're loading your case in parallel, then if you have a reader that is compatible with the Auto Partitioner, so the Plot3D reader is one. It covers a lot of structured solvers. We do export to that format, which is kind of a standard. And we also support Auto Partition for the Overflow 2 solver. Then all you have to do is select the Auto Partition option over here. And that setting is going to be remembered from session to session, because we're going to assume that you want to continue to use the same setting. And currently with FieldView 21, you will be able to tell that the Auto Partitioner has done some repartitioning, because the list of grids is going to change and you're going to see more grids of smaller dimensions. I'll come back to that in a minute. Next, we've also added support for ghost cells. As we are creating new partitions, this can sometimes, for some variables, define some new variables, user-defined variables, create some discontinuities. If you have user-defined variables with spatial derivatives, and so it may show up with small gaps of about the size of a cell. So this is really showing up here on a coarse case to really highlight the effect. If you ever encounter this problem, and if you care about closing those gaps, then all you have to do is add ghost cells at read time. You can either do 0, 1, or 2 layers of ghost cells, and you can see that with 2 layers over here, we're totally closing that gap. But again, this is only if you have user-defined formulas with spatial derivatives. All the native variables that you get directly from the solvers are not going to be affected by these new partitions. Finally, I want to say a word about one of the new capability we've introduced in FieldView 21 that is related to MPI. FieldView comes ready in its package with OpenMPI, which is an open source implementation of the MPI protocol. So the way it works is that we have the field client that talks to the FieldView controller, and through MPI, the controller is going to control the work done by all the FieldView processes, and then they are going to return back components of portions of the surface that need to be rendered by the FieldView client. So we have a new module between the FieldView controller and OpenMPI, which we call myFVMPI. And what it does is that it lets you use any MPI you may want. If you have an HPC system, if you care about parallelization of your tools, you probably have an MPI that has been compiled and customized specifically for your HPC system. Maybe it is Intel MPI, maybe it is MPitch, really with OpenMPI. Those are the 3 most common distributions for MPI. And so with myFVMPI, the idea is that you can use any MPI that you want. And you can really rebuild myFVMPI against the MPI you have and use your own so that you get the best performance with FieldView Parallel. Just a quick word on future work, since we're continuing to improve this new capability. First, things we are currently working on will be hiding the new grids in the next version of FieldView. So I was mentioning earlier that they currently show up as additional grids in your list of smaller dimensions. The problem with that is that then when you navigate through your mesh, maybe you want to create a computational surface for a given grid. If those grids are coming from your topologies, maybe you know that grid 3, I don't know, is at a particular spot in your geometry, and so you want to work on that. You don't want grid 3 to be split into 3 and 4. So what we'll do is that FieldView will continue to do the auto partition under the hood, but to the user, the numbering, the grid dimensions, everything will be preserved and the work will be fully transparent. So that work is pretty significant, but it's almost done. So it will be in the next version of FieldView, that's for sure at this stage. And another thing we're currently working on is adding a report of the load balancing, and this way, if you have gains through the auto partitioner, we'll be able to tell you that. And also, we are considering adding this capability to more readers. So again, for now, it's limited to overflow and the Plat 3D format, which covers a lot of structured solvers. But if you have interest in a solver that is not covered by this, let us know, and we'll consider adding support for it if our technology is compatible with that format. All right, before I wrap it up, just want to encourage you to go try it for yourself. If you want to learn more about this capability, we have a post on the news section of our website. Over there, you have full details. And if you scroll down on that page, we're even providing code samples for scripts. If you want to run your own benchmarks to see what improvements you get with the auto partitioner, got code samples over there that you can download. And we also provide explanations on how to customize those code samples to adjust them to your own workflow and your own data sets. So that's very easy. And then the auto partitioner and the myFVMPI capability I've just mentioned, they both require an optional license for FieldView Parallel 32 and above. So that's really the license that we have for customers who run a lot of parallel jobs and want to get the best performance. So if you don't have yet such a license, you can contact Raja and he'll hook you up, and it'll provide you with an evaluation license for you to try it. All right, with that, Raja, this is the end of the material I wanted to cover today. So I'll get back to you in case we have any question.
Yeah, there's one question here. Let me try to find it here. One of the questions was future possibility for having the auto partitioner to read FVUNS files from star CCM plus.
Okay, yeah, that's an interesting question. So all the cases that I've presented so far are structured grids, and there's a reason to that. When you work with structured data, it's easier to use the IJK data structure to skip portions of your file. And so this is the trick we're using with the auto partitioner to limit the overhead we have, and so get really some speed ups from the auto partitioner. The FVUNS format doesn't make it that easy. So the technology we will have to develop will be quite different. So this is something we're considering, but it's going to require a different approach and probably more investing in some read time upfront to create the partitions before you read the data. So again, this is something we're considering, but that will require significantly different development work.
All right, thanks, Yves-Marie. Another question, how do I know what version of FieldView Parallel do I currently have?
Okay, all right, so let me show you that directly in FieldView. Okay, so I've got FieldView running in the background here. With FieldView 21, another major change that we've done was to change the licensing module, the licensing manager that we use. We know based on RLM. And so that gave us additional capabilities, such as the ability to set or check your license from the FieldView interface. If you go to Help, we now have an entry for FieldView licensing that gives you this new panel. And right here, I got all the properties for my license, the expiration date, license number, which is useful when communicating with our support team. And right there, it says parallel 32. So if you have more of a standard license, that will say PAV 8. So that's how you'll tell. If you have PAV 8 auto partition, the auto partition option will be visible but disabled. And you'll need to go to 32 or 64 to get that enabled.
Thanks. And another question just came in. Is the Auto Partitioner also support AccuSolve files like, and then it says star.fv?
Yeah, so that's the same answer as the earlier question. This is actually the same format that AccuSolve exports to. It's the .fv is the FieldView AVUNS. So star CCM plus, Fluent, a lot of commercial codes that are unstructured export to that format. And because it is unstructured, that will be different work, but this is something we're considering for the future.
Thanks, Yves-Marie. That's all the questions we have. And yeah, do you have anything else, Yves-Marie, or should we wrap up the webinar?
No. Just want to thank everyone who joined us today for this presentation. We can stay a few more minutes if people want to type in more questions. But yeah, if people want to leave now, feel free to go. So this webinar has been recorded, so it will be available as a recording on our website pretty soon. So if you want to share it with some of your coworkers or get back to some of this material that wasn't clear the first time, I hope I was clear, but in case I was too quick on some sections, the recording will be available. And also we have more details available in the section that I mentioned over here in the white papers that is in the news section.
Yes, and if you want more detailed, in-depth conversation with us, feel free to set up a meeting with me, get online with you to discuss this further, to see if this might be a good fit for you. With that, thank you all for joining us today, and have a great day.
Thanks, everyone. Thank you, Raja, for hosting this webinar.
Thank you, good. Thank you all.
All right, goodbye.
Bye.